doing the story wasn't a critical part of this. We'll talk a little bit more about why I believe that's so important. Even if you don't have a good story, a couple of you didn't have a great story, but at least in your analysis, your paragraphs talk about 2 or 3 papers in the same paragraph. Okay? If your paper was, here's a paper number and here's a paragraph about it, repeat that 50 times, that's really not a survey paper. We call that an annotated bibliography. It's a thing, right? And that's all it really is like, here's a paper, here's a summary of the paper. And when we get to talking about your oral exam today, we'll get to why that's so important. And then some of you had very short things that really weren't quite there. I know a number of people have been sick, there's been some issues, so I'm giving people time. If your paper, your survey draft was very, very short, I'm not sure, because apparently some people are having a hard time uploading them, Steve. And somebody else also said they tried to upload it and it didn't show up. I don't know what that means, but maybe I set some absolute time limit in Canvas. After a while, it just stops, right? The assignment was due 2 weeks ago. So if it's worth 0, maybe it doesn't do anything. So I might put another one up today just to give you a chance to turn in something. For those of you who did your reviews, thank you. From the journals, I got the feeling most people found the reviewing process actually enlightening. Unfortunately, so if you only got 1, you didn't get as much enlightenment. If you want some more, as soon as other people turn in papers, I can give you more, but I'm also not going to make you do more. They had their shot, they didn't turn their paper in time, they don't get as much review. So if you want to review another 1 or 2, let me know, I can get you more, but if not, that's okay. I have not yet reviewed your reviews. I will do that, and I will give you feedback on your reviewing, but I'm going to do that until after I'm done the paper. So first I'll get through all that. From the comments I saw in the journals, I think most people did a pretty good job in terms of what they said was their process for doing the reviewing. I recognize your reviews are sometimes pretty far, your background is very far from the paper you're reviewing. That's okay. That also means that if you're looking at the review feedback you got, you have to make the decision, do I listen to them or not? If they kept saying, I have no idea what you're talking about, but they're also not your audience, that might be okay. But in the first page, you shouldn't have lost anybody. Right? In the last page, everybody should understand your conclusions probably, but definitely in the first page, the beginning should be so broad that everyone understands it. So if you're losing them too quick, you want to make it broader to bring a few more people in. And then they can decide if you're going to take the effort to get through the more technical stuff you get through. But the intro should be pretty generic to get a lot of people in pretty quick. I think there was at least 4 I read so far whose intros were really not intros. And I'm guessing you read a survey paper among your reading that started with, here is our survey methodology. Like, here's the papers we reviewed, here's how we found them or whatever. That's not a bad section to have in your survey paper. But is that going to make you want to read the rest of this paper? Probably not. Talk about the problem, the area, right? And then you can have a section on methodology, right, where you tell me how I selected papers, okay? It's also important if you selected papers from Google Scholar by saying, I use the top N out of the Y lists, you have to include that list in your paper because Google has no history for those lists. You can't find out what was in that list last year, right? So it would be very confusing to people if next year they read your paper and you said you use the top 20 journals in the subsection and they go look at it and you didn't use 3 of them because last year those weren't in the list, right? So you should have a list. I use the following, which were determined by the top 20 or top 10 or whatever, right? So I'm pretty clear about that stuff. If you feel it doesn't make sense in the actual content of the paper, you can make them bibliography references, right? Because you can reference the entire journal. It's a little bit weird. Or put it in an appendix. You don't have to have everything in the main core of your paper. Some of you really have long, detailed things. You can put stuff in an appendix. So you still have lots of restructuring. I have not yet set a deadline for when the final version will be due. I realized that I gave feedback today to those slightly more than half that I finished. They will have a little bit more time. I might actually give them an earlier deadline and then give everyone else a later deadline if I don't get them finished by Wednesday, which is my goal. But my goal was to have them done last Friday too, so much for goals. So my comments are directly embedded in your document. If it's a PDF, there are PDF comments on top of it. And there are really 2 kinds of comments. Stuff highlighted, generally in red, and then little text boxes. The text boxes, depending on what PDF reviewer you use, you have to click on and open them up. They are generally in the vague area of where the thing is. They're not tied, not always tied to a particular point, which depends on your viewer and my viewer and how the two interact. I use Max Preview, so if you're using Mac Preview, they'll be at the right line. If you're using Adobe, they'll be somewhere in the neighborhood of the right line. If it's highlighted, it means something was funky. Okay. Sometimes I would tell you what's funky, but after a while, if I've told you 3 or 4 times, I just start highlighting them just because I happen to notice them and they pop out at me. Other times I highlighted them and there is no comment and I have no idea what's going on with them, because sometimes I had no idea what was going on, and after a while I don't put another comment saying huh. But if you get a comment that says huh, H-U-H with a question mark, that's pretty much what I said when I read it. It's like, huh? I have no idea what this is trying to tell me. I can't make suggestions on how to fix it if I can't begin to understand what you were trying to accomplish. So you're free to come see me during my office hours or scheduled time. We can talk over what those are. Or you can highlight the paper, like do a little screenshot and say, what is this trying to tell me? And I'll try and make sense out of it. If you send me just the comments, I may or may not be able to figure it out because I won't have the context. Although I guess I have the paper, so I can always look them up. But, so hopefully that added feedback. Some of you also said, what do you do when the reviewer and the instructor disagree? The answer is go with your gut. It's your paper, not mine, not your reviewers, right? So you may do something that is not what I said in class, and you may convince me. Some of you actually did. Some of your papers were not what I was expecting you to do based on the feedback you gave me the first round, and it worked fine, right? It's always hard to tell what story will work until you see it, right? So I can't tell you, no, don't do that. I will make suggestions. If I tell you, no, don't do that, then don't do it. But most of the time, if I make a suggestion, I'm not telling you, don't do this. I'm just trying to make a suggestion that might be helpful. But there are definitely times when people's stories went ways I didn't expect, and it's perfectly workable that way. And if you're not sure, so generally I gave you some high-level comments about your storyline. Some of them need work. If at the end, especially if your advisor is telling you A, and I am telling you B, go with what your advisor tells you. They are your advisor. They are spending more time with you and paying the bills. I'm just giving you advice. So if you have your choice of your gut, your advisor, me, or the reviewers, I would actually list them in those orders. Those are your priorities. What you actually believe is right. Even if you and your advisor disagree, your job is to convince your advisor if he or she doesn't agree with you. And if you can't, then maybe you give up. But you shouldn't just say, I'm going to do what my advisor says. You should, if you really believe it, try and fight for it first. But recognize there's a point at which you stop doing that as well. Because if your advisor says it's a bad idea to keep going down this path, I won't fund you, they won't fund you. Right? Now, if they're not funding you already, you might say, I don't care, I can go down this path. Well, then they might just stop working with you. And so some advisors, more so than others, want you to listen to them. So take that in consideration if they're giving you feedback on the journal. Only one of the ones I read so far actually said in what they were doing what their target was. So if I know what your target is, I would have actually given you more feedback. If you say, my target is IEEE communications, surveys, and tutorials, I will be looking at it from that point of view. If you say, I'm aiming for a conference, which is what one of the papers said, right? Then I will make some comments relative to what I've seen for that conference's point of view. I can do a little bit of research, but I mean, most of you didn't say, that's okay, because you can shop it around and sort of figure where it goes, but there's slightly different styles. Any questions on the second draft, the third draft elements? So I will eventually post it and give people deadlines and timelines, but it's not a critical issue. So last class then, I'm now going to jump onto today's material. Last class I started into clouds, but I didn't get very far. No, it's not up there. So I don't think I did these slides. Did I do these? 10 benefits of your research? As best I could tell, this is about where so here's the slide before that. I talked about services, a little bit about the comparison, and then I think I went to why to use it. So for those of you who already know all of this, my apologies. We're going to go through it again. Have some more candy, distract yourself. Maybe pull up your paper and work on it or something where you ignored me. But we're going to talk a little bit about using Amazon AWS for your research. And everything, again, as I said last week, everything I'm going to describe today, I'm going to do Amazon AWS. Even for the assignment, which I will be posting this week, which after the end of today's class, I'll explain what it is. I haven't actually written it up yet. If you would rather do it using Google Cloud, because either you already know AWS and want to learn something new, or you already know Google Cloud, you don't want to learn AWS, I don't really care. We also have free credits for Google Cloud, so you could use that for this research. I just didn't go through all the instructions and write them up and how to do that. I use AWS way more often, so I'm just going to use that as the example. But just about everything I'll talk about today, almost all those services exist within Google Cloud as well. Most of them exist within Azure, but I don't have an Azure account that I can get you free access. They gave the company I work with free, but not students. So first, why do you want to use AWS/the cloud for your research? First, you have a wide range of hardware to match your research needs. Your lab, your faculty's lab here may or may not have stuff that you want. Even if they have everything you want, it may not be as easy for you to use. There are many pre-configured machine images to choose from. So if I want a machine with TensorFlow installed, it might actually be easier to just go to Google Cloud or to AWS and say, give me a machine with a machine learning instance already configured with with TensorFlow and Docker images and stuff, and I don't have to worry about installing everything. If you do it yourself and you own your own machine, great, you can learn how to do all that installation stuff. If you want to learn how to do all the installation stuff, you can also do that on AWS because you get full root access to your VM. That's good and bad. You can destroy things if you want. It's your machine. You can't destroy Amazon's cloud, but you can like completely remove your file system if you want. If you haven't figured out how to lock yourself out of your AWS instance yet, I can easily show you how to do it. I've done it multiple times by setting up firewall rules that don't let you reach the internet anymore, in which case your unit stops talking to itself or to anyone else, right? You basically say, oh, only local communication. Oh, then how did my SSH work? You get free accounts. So if you sign up, which I sent email about, just make sure you had the links, which I'll mention in class as well. You get $100 worth of credits for free, maybe $150, depending on exactly when you signed up this semester. And I can get you more in the future for your research. You can probably get another 100 outside of this class if we do it. If you're doing it right. Your advisor can also, or you can write a proposal to Amazon to get free. Faculty research grants are like $80,000, $40,000 worth of credits. They're pretty hard to get, but getting $1,000 for your research, every student I know who's asked for that normally ends up being able to get their advisor to get that. Campus actually has some ways of getting you some extra Amazon credits because if you don't know it, we actually buy, Campus pays for a lot of Amazon stuff, like all of our web services now are running on Amazon and things like that. So if you do actually use it for pay, you pay per use. You're only charged for the disk space, CPU, and bandwidth that you use. From a company point of view, that was very useful. Sorry, I gotta take my head off here. It's too hot. So you don't have to pay as much. So for some of the projects, we actually paid a small amount. For one of my students recently, went over the $100 we needed for their work, but that's okay. It was like $140, so I paid $40. We still got our work done. It's pretty easy to scale. Abhi, one of my previous students, did a large chunk of the last year of his thesis on it, in part because, I'll come back to some other reasons, but the CPU and bandwidth limitations, like we paid like $70 for all the work he did. In terms of the amount of time it would have taken him to set stuff up, coming back to this pre-configured machines and stuff, right? It would have cost more than $70 worth of his time to set up all the machines, right? So cost is actually, I don't care if you have to pay for it, if it's also saving money someplace else. But the other reason the student did it was actually the instant scalability. After doing some very simple processing locally, it was easy to scale up and use 50 machines, which is a little harder in my lab, although I have 50 machines, they're heterogeneous. So it's not easy to say, go make it run on all 50. There's 50 different machines, you configure them, you'd waste a lot of time. So it was pretty easy to scale stuff. Another one of my students did his work on AWS and actually it had to be on the cloud because you're measuring cloud performance and whatever. So it's very easy to scale various things, and I'll talk a little bit about how to do some of that. Very high reliability with infrequent outages, at least so far. The data is redundant in the cloud, so if Amazon East even has a problem, you can just move to Amazon West and you generally don't have to worry too much about anything going on. Their reliability is measured in multiple nines, like 99.9995% uptime or whatever. It can vary a lot, but your internet access to them is probably way more unreliable than their internet access or their reliability. All the services have some levels of built-in security. So one of the other nice things is their images, when you spin up one of their images, when you first spin it up, you can be pretty sure it has all of the patches and things applied to it. The default for most of their images, in fact, they're all set up to auto-update for security. You can disable it because sometimes updating security patches break your work and you don't want that to happen, in which case then the security stops getting applied. But they at least start with built-in security, and most of the services have pretty good security built into them. There are API libraries available in all major languages. which includes what you might not consider major languages, things like R, Go. There's stuff for all those. So in whatever language you're starting in, there's a pretty minimal learning curve. Some features are naturally more suited towards some languages. So there actually is a C interface to a whole bunch of stuff, but it's really painful to do like JSON parsing in C. So that's the JavaScript object notation. So you got to balance out what you're going to do. One of the reasons I like Amazon, first of all, is because it's the first one I learned. They've been doing it for about 15 years. They also have many customers, so it's actually a saleable skill. As I mentioned, my student did one last part of his thesis. He wanted to have the skill of having done it on AWS. He could have done it in my lab. Might have been slightly cheaper, might have been more expensive depending on his time. But either way, now when he graduated, he could say, I did this part of my thesis in AWS. I've done this and this and this. So when you go to look for an industry job, that skill might actually be a saleable thing you want to get for an internship or for a job. So in that reason, it's worth doing a little bit of that just so you can sort of say you know it. The bad thing is things change very fast. If you were really good at AWS 4 years ago, a number of things have changed. Lots of it's still the same, but a number of things have changed, so you're going to have to keep staying up. So I'm going to very briefly talk about 4 core elements that I think you might use in your research. There's a whole lot more I will briefly touch on. So what I will call Amazon Web Services stack. The first 2, I can't imagine you doing research on AWS without them. The Elastic Cloud Service, EC2, and the Simple Storage Service, S3. This is pretty much where you compute and where you store. If you're going to use EC2, you probably have to use S3. There's a few other things you could do, but you really wouldn't want to from a price point of view. The other 2 are very simple things, but if you need to do very simple database services, because you have lots of data and you want to make it efficiently accessed, the Simple Database Service is very easy to use, and the Simple Queue Service, which is a way of sort of queuing up data between things, can also be very easy. So these are the 4 that my students have used that are pretty the easiest. So EC2, the Elastic Compute Cloud, is a sort of on-demand grid of computers. They basically have this idea of there's a bunch of machine images. By a machine image, we mean that it's really a virtual machine that's running an operating system and some apps. So you basically, to use this, you create a machine image, you deploy the image to S3, once it's deployed, you can then start it up. So you're going to start one or more regular instances, and then you SSH into it and you use it as a regular machine. Or once it's started up, there's web services and you connect to it through web services port, whatever you set it up to do. So the main options that you have in this are whether or not you're going to have dynamic or static IPs. There's a price differentiation. How many cores you're going to want to have. Where you want it to run. Do you want it to run in North America's east, west? You want it to run in Singapore? You want it to run in Europe? And what kind of persistence you're going to have in terms of the Elastic backing store, where you're going to store your data. So some very simple examples for your EC2, sort of batch processing. If you want to run an experiment that, say, needs a lot of memory, right, and you want to run 10 or 12 versions of this, okay, so in my lab, I have one machine with more than 256 gigs of RAM. I have one. So if my students want to run 3 or 4 experiments that need 300 gigs of RAM each, or 380 gigs of RAM each, you can't run them all, so then you have to run them sequentially. But I can go to EC2 and I can rent or buy a machine that has 384 gigs of RAM, which is actually I think the biggest you can get right now. But I can have 10 of them. So I could set up a machine and basically have it run the same code on slightly different data with a different parameter, and then all of them, I could run 10 machines at once. So you get them all configured, you get them running, and then you basically spawn off instances, and based on some parameter, they will run themselves. It's another variation of that is where you run them on subsets of the data. So it's not memory limited, but I want to run a bunch of stuff in parallel. I break my data up into 10 giant chunks, and I run in 10 processors. I break it up into 50 chunks, I can run in 50 processors. And the difference between 1 and 50 is literally what number I type in a box and I say run. That's especially true if I've structured my code right. So there's a little bit of effort there where the machine has to know what is this instance number and therefore what range of the data it works on. But if I know I'm going to have 50 instances and I tell everyone, take your instance number, which is one of the parameters you can get with a function call, and then you work on the ith out of 50 chunks, then you know what it is. Another very common way is if you do everything with random data, then it doesn't matter. Then every instance is the same. You go to a random subset of data, go do something. And it's common in machine learning to do a bunch of random runs, so that becomes very easy to do. The partitions that separate the data are stored in a configuration file to sort of say, this instance has this partition of the data and do things. If I'm actually doing things that need web services, so I'm looking at anything where I'm going to have like REST APIs or whatever, all the instances are configured with sort of the same code, and then I can do more instances can load as I need load balancing. So from a company point of view, if I want to do web services, I can automatically scale. If I hit this load, spin up a new machine. When it hits a new load, spin up this machine. Oh, look, the loads are small enough, kill a machine, right? Because they're storing all their shared state in either the storage cloud or the database. It doesn't matter if machines go up or down. And so that gives you true scalability. So you can do some of that for your experiments. If you make your experiments some mix of web and batch processing, so web services control what gets fired up, then you can do sort of a mix where the web services fire up some compute code that happens and then puts all your results together. So those are all very simple. If I do it with web services, the DNS servers automatically distribute requests between the load balancers, so that literally if I ask for www.uccs.edu, that actually gets rerouted into Amazon, and it's one of n machines where n depends on how many people are hitting www.uccs.edu. So as the load goes up, if a bunch of people start trying to do registration, there are more web service instances needed, then there will be more servers at Amazon, and when you ask DNS, what does www.uccs.edu mean, it will give you different answers depending on who you are and what the current loads are. So it dynamically changes the name to number mapping to make all that stuff transparent to the end user. So it makes it pretty easy to scale stuff up using that kind of model if you really are doing it. May not be relevant for your research. The first is, I think, more common on my side of the research, but who knows where your research will go. So underlying dealing with this for almost all of them is I have to have somewhere to store my data, especially if they're running in parallel where I don't control where they are. You don't want to really think of this as one giant file system. It's not really a file system. It's more generic than that. Simple storage allows us to store large media and everything else. But it was really designed for storing larger blocks of data, not just really small items. So if you think of it as a file system, think of it as a file system with a very large block size. And the reason it's that is because it actually wants to transfer blocks between the storage servers and the compute servers in large blocks. So it will do them in this sort of function. So instead of a file system with names, everything is based on unique keys, which is like a hash of stuff. And I do puts and gets into buckets based on unique keys, and buckets, or think of those as folders. So if I think of a folder plus file extension, the bucket is the name of the folder and the unique key within it. The unique keys are actually unique across buckets. They're supposed to be unique across all buckets, so it doesn't matter as much. It has both private and public access and groups, so you can do the sort of storage permissions you're used to. And it has support for very large objects. One of the reasons one of the companies I've worked with uses it is because we have this unfortunate limit of a 2 terabyte file, and their files were bigger than 2 terabytes on a regular basis. It made it much easier for them to not just store them in S3 because they can have it as one big file, but to then do the processing in the Elastic Cloud where they could break these giant files up into pieces. But if the file is sort of a streaming file, you can imagine video things, which is the space we work in. Video files can get very large very fast, and S3 allows you to keep appending to an object, right? So not only do I get the object, I get a handle to it, I can keep appending to it, so I can add to the back end of a streaming file while somebody else is already reading off the front, which approaches the queue stuff we'll talk about and it becomes related. Image video storage on S3. Once you put your media up there, S3 will serve it, which is common for content distribution. This is also common for people trying to make it so that my data is replicated. S3 will transparently speed up access to your data based on where it's getting accessed a lot. So they literally do the equivalent of prefetching for you so that they get the services. If they're going to ship one block from here to Tanzania, and the first block they ship, that's it, ship a block. You ask for the next block in order. Not only do they ship the next block, they ship the one after that. They start prefetching because it's to their advantage to maximize their bandwidth during transport, and they expect now you're going to use it. Just like any OS does prefetching for reads, they start doing some of that as well. So that can make it pretty interesting. You actually only pay if you read it. If they prefetch a block and you never touch it, you don't pay for it. But reads are 10 times cheaper than writes, so you can do a lot of reading for each write. You can also use them to serialize your Java objects. They have a defined keys, which makes it easy to deal with them in and out of S3. If you're dealing with small Java objects, it's important you actually think about how many objects fit in a bucket and do the right bucketing structure. Otherwise, you're a little bit inefficient because it'll spread them out across buckets, which means you don't get the prefetch reads, because prefetches are based on their buckets, right? So you might want to think about how to serialize them inside of that to get a little bit more efficient, but read them back when you want. While I'm not going to have any slides on it, Amazon has another storage, actually it's 2 other levels of storage, but it has a level of storage called Glacier, right? And as its name implies, it's glacially slow. It is super big and very cheap as long as you never read from it. Writing to it is very cheap, and the expected read time is 7 days. So if I want something, it may be 3 to 7 days before I get it. I think 3 to 7 is where this. So 7 is, I guess, the maximum. And there's I think there's 2 pricing tiers. But for what we used it for at my company, Glacier was our critical offsite backup. We hoped to never use it, but when we shipped software, we wanted to make sure no matter what happens. So we had an offsite backup, but who knows, right? Maybe that goes too. This was partially paranoid after my partner's house literally burned down in the fires, right? And that was our offsite storage. It's like, wow. And cinders were falling on our company's office building. It's like, wow, we could have lost everything this week. Let's have one other backup way offsite. And so we used Amazon Glacier, which you just write stuff to, and if you never read from it, it's very cheap. And if you read from it, you pay a reasonable price. So that was our sort of offline extra backup. And if I had really big objects, I might think about that again, but I don't have stuff I financially depend on in my lab as much. So, Simple Database Service is a very basic database and indexing service. In fact, I would not quite really call it a database, but that's what they call it. I would just view this as a giant key value pair, right? Which is really not a database in my view, but it's okay. So you have a key and some attributes. It creates flat file databases with auto-indexed tables. Okay, you can't do things like table inversion and you can't do relational joins or any of this other stuff, but it's pretty simple. And if you notice, right, it's based on some flat tables with keys, which is what their storage is. So this really is just a quicker way of getting through your data. One common way of doing this is to associate your file names with your keys. Right? So you had a file name you wanted to put in Amazon, but the only thing you actually get to use for putting and getting are keys. So if I want to actually remember something by file name, what do? Well, I put it in the simple database where the index media is stored on S3. I have the same key, and here I have all the metadata attributes. So if I want to be able to look something up by its name or any of its other metadata, I would do that. And I can also use it as storage for non-nested data. So if I really have a bunch of flat files, things that might be small and therefore I don't want to actually use S3 for them, I can use them in the simple DB. I thought I had slides on simple Q. I guess I don't. Because, well, maybe I do after this. But so Amazon has a whole lot of other features. So I've touched on a few of them here. But inside of compute, besides EC2, there's EMR. It's elastic matching. EMR, elastic match reduce. MapReduce, which actually I'll talk about a little bit. Amazon Virtual Private Cloud, Amazon Kineticist, Route 53, Direct Connect. All of these are specialized compute services. Most of them are for web service-oriented things at company level, but they all provide some level of compute storage. Besides S3 and Glacier, which I mentioned, there's CloudFront, which actually I use all the time. CloudFront, if you run web services and you run websites, CloudFront is depending on who your service provider is, a very cheap or maybe even free content delivery network that will speed up your website. By basically using Amazon's web services, you get this CloudFront that will cache your website, and when people ask it, they play games in DNS space so that instead of your DNS going to your machine, it first goes to their machine that says, is it my local cache? And if it is, deliver it, otherwise go here. And if you deal with a global distribution or just lots of people hitting you, you'd want to use that. So when I do web stuff or apps for conferences where we'll have nothing happening on this website for weeks, and then for 2 weeks, 3,000 people hit the heck out of it because it is their conference app and they do everything through it. And those kinds of things, you really need to have that content distribution network, especially because if it's in Europe, right? I don't want my servers here sending everything back and forth across the pond. That happens naturally with CloudFront. They have a bunch of database things. So in addition to the Elastic Cache, which I didn't mention, they have this thing called Redshift. I've actually never used it. RDS and Dynamo. So I think Redshift is their NoSQL Mongo type structure. I'm not sure. One of these two is, and the other is a relational database. RDS has got to be relational database services. They have a bunch of application services for making any of your app stuff go faster. So they have things to speed up search. They have things to do transcoding. So if I want to have video of one kind in and video of another kind go out, they'll do that for you automatically, which is where those very big files from one of the people I worked with goes from. They wanted to take in raw, compressed files, which stream in at huge sizes, and then transcode them to actually 6 different transcoding speeds. So if you think about streaming from like a 4K video sensor, right, streaming at 30 frames per second, and then having it come out at HD, whatever, when you do YouTube, right, you get a little pull-down menu with different sizes. Somebody's got to do all that transcoding. Google does it for YouTube, but you want to do it yourself, you get to do that with Elastic Transcoder. And then there's a whole bunch of deployment things for doing Beanstalk for web stuff, CloudWatch, identity management, a number of other items at the top level. And this is only about half their services. So AWS has a ton of things. If you're really a business trying to build on top of stuff, there's a ton of things to make it go fast. So first things, which is related to your assignment. So I'm going to make the assignment a little bit more general. I'm basically going to ask for you to show me by recording your screen, because that's the easiest way. I was trying to figure out before, how am I going to know if you actually go through all this? I want to know that you can spin up a machine, log in, run some code, right, and get some results. Okay, so I'm gonna and I'll write this all up tonight or tomorrow. But basically, you're gonna log in, get to the point where you can create an instance on AWS or Google Cloud, log into the instance, run code in whatever language you want, showing me you ran some code on some data, and then get the resulting data back off of it to your machine. And the easiest way for you to show me that you can do all that is actually to do a screen recording. I will also post instructions on how to do a screen recording. Is anyone here using something other than Linux, Mac, or Windows? Anyone? So yeah, I'm pretty sure. So anyone running on Linux? Okay, so I'll make sure I do all 3 for how to screen record in any of those, just to make sure it's straightforward. Anyone not know how to screen record? Okay. Screen record, video. I want a video file. So how many don't know how to do a video? Okay, fine, then I'll make sure I post instructions. Okay, and by the way, I do screen recording for every class and been posting them just in case you haven't noticed that. But so let's start with firing up instances. So I'm actually going to start with this link because I have to do this. I forgot to start up today in split screen mode, so let's go do, yeah.